Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for February-March 2024. So let's get started. Question 1 says, figure 1.1 is a speed time graph for the first 5 minutes of a bus journey. The question wants us to describe the motion between the times from 0.9 minutes to 2.9 minutes. So from 0.9 here to 2.9 here. The graph was a horizontal line on a speed time graph. That means a constant speed since the gradient is equal to 0. So acceleration is 0. So constant speed. Number 2 says from time 2.9 minutes to 3.5 minutes. So from here to here, the speed was decreasing in a straight line. So it's constant deceleration. 3 says from time 3.5 minutes to 4.5 minutes, from here to here the speed is equal to 0, so the object is at rest. Part B says another bus travels at a speed of 8.9 meters, the brakes apply a constant force and the bus stops in a distance 23 meters. This bus has a mass of 18,000 kilograms. Calculate the kinetic energy of the bus before the brakes are applied. So using this speed, kinetic energy is equal to half times the mass times the speed squared. So half times 18,000 times 8.9 squared. That gives an answer of 712,890 joules. So we can approximate this to two significant figures since the numbers are to two significant figures in the question. So we will write 7.1 times 10 to the power of 5 joules, or just 710,000 or 710 kilojoules. Double I says calculate the force applied to stop the bus. Here we have two options. The first option is using kinematics and the equations of motion. So we have the initial velocity is 8.9, the final velocity is 0, and the distance traveled was 23. We can get the acceleration and then use force equal mass times acceleration. Or the shorter way, we can say that the work done against the resistive force is equal to the change in kinetic energy of the bus. So force times distance is equal to the change in kinetic energy. So the unknown force times the distance 23 meters is equal to 712,890, the actual number, not the approximated number. Then we divide by 23. So that gives a force of 30,995.217, which we can approximate to two significant figures as 3.1 times 10 to the power of 4 newtons. Question 2a says define impulse. It is the product of force and time derived from the equation of force. Force equal change in momentum over time, or impulse over time. So time is multiplied by force to get the impulse. Question B says figure 2.1 shows a rocket and its exhaust gases. The exhaust gases are emitted from the rocket with a velocity of 1400 meters per second and at a rate of 2800 kilograms per second. So we have mass and we have time is 1 second. Part I says show that the force exerted on the rocket by the exhaust gases is 3,900 kilonewtons and state the equation. So the equation is that the force is equal to the change in momentum over time, or the mass times the change in velocity over time. So we substitute by the numbers here. The mass is 2,800. The final velocity of the gases is 1400 meters per second. And the initial velocity is 0. And the time is 1. This gives an exact value of 3,920,000. So the last three zeros, that's the kilo Newton. And we have here 3,920, which is approximately 3,900 kilonewtons. Part double I says calculate the maximum mass that this force can lift from the ground. Ignore air resistance. So for the rocket to launch upwards, the force upwards must at least be equal to the weight. So we say that the force is equal to the weight, which is calculated mg. So we have the calculated force of 3,920,000 is equal to the mass, which is required in the question. Then we multiply by G 9.8. So to get the mass, we divide the other side by 9.8. That gives a mass of 400,000 kilograms, or we can state it in standard form. So 4.0 times 10 to the power of 5 kilograms. Question 3a says a car has a weight of 13,000 newtons. The car is supported by 4 tires. The area of each tire is 0.016 meters squared. Calculate the pressure on the road due to the weight of the car. So we have the equation pressure equals force over area. So we divide the 13,000 by the area of one tire, which is 0.016, multiplied by the number of tires, which is 4. That gives a pressure of 203,125. So we approximate this to 2.0 times 10 to the power of 5 Pascal. Part II says, explain in terms of particles why the air pressure in the tires increases when the car travels along the road. So first we say that the friction increases the temperature of the tires. So air particles gain kinetic energy and collide harder or with greater momentum and more frequently with the walls of the tire, increasing the force per unit area. So as momentum increases and the collision rate increases, the force increases on the inside of the tire, which increases the pressure. Part B says a gas cylinder contains helium gas at pressure of 2.0 times 10 to the power of 6 Pascal. A volume of 0.026 meter cubed of the compressed gas is released from the cylinder. So this is not the total initial volume. This is the volume that gets released from the cylinder into balloons. Each balloon contains 0.015 meter cubed of helium at atmospheric pressure of 1.0 times 10 to the power of 5 Pascal. The temperature remains constant. Calculate the maximum number of balloons that can be filled. So we have two pressures and the initial volume. The final volume of the gas is not given. This is the gas volume inside one of the balloons, not all the balloons. So this is not all of the gas. So using P1 V1 equals P2 V2 at constant temperature, we substitute 2.0 times 10 to the power of 6 multiplied by 0.026 is equal to 1.0 times 10 to the power of 5 multiplied by the new volume of the total gas. If we divide by 1 times 10 to the power of 5, we get the value for V2. It is equal to 0.52 meter cubed. And this is equal to the number of balloons multiplied by the volume of one balloon. So 0.52 is equal to that. Then we divide by the volume of one balloon to get the number. So the number is 34.666. So we can fill about 34 balloons. Question 4a says define specific heat capacity. It is the energy needed to raise the temperature of a unit mass, which is either 1 kilogram or 1 gram of a substance by 1 degree Celsius or 1 Kelvin. Part B says a volume of 0.0024 meter cubed of oil is heated in a pan for 7 minutes. The temperature of the oil increases from 20 to 180 degrees Celsius. The density of the oil is 910 kilograms per meter cubed, and the specific heat capacity of the oil is 2000 joules per kilogram degree Celsius. Calculate the mass. So the thing that is directly related to mass is density. So calculate the mass by multiplying density by volume. Here we have 910 and the volume was 0.0024. That gives an answer of 2.184 kilograms, which we can approximate to two significant figures since the numbers in the question are two significant figures. So it's approximately 2.2 kilograms. Part II says calculate the energy required to increase the temperature of the oil. We can use the energy equals to mass multiplied by the specific heat capacity and the change in temperature. So we have the mass, we use the real value 2.184 multiplied by the specific heat capacity given in the question 2000, and the change in temperature between 180 and 20 degrees also given in the question. That gives an answer of 698,880, which we can approximate to two significant figures or three significant figures, maximum 3. So we have 6.99 times 10 to the power of 5 or 7.0 times 10 to the power of 5, and the answer is in joules. Part III says calculate the power required to supply the energy calculated in BII. So the equation is power equal to energy divided by time. So we divide the actual energy 698,880 by the time, but it should be in seconds, not in minutes. So we multiply 7 by 60. That gives an answer of 1664, which is approximately 1700 watts. Question 5, AI says table 5.1 shows applications of regions of the electromagnetic spectrum. Complete the second column of the table with the region of electromagnetic spectrum used for each application. Choose from the regions in the list: gamma rays, infrared, microwaves, radio waves, and ultraviolet. Each region may be used once, more than once, or not at all. So we have the application and the region of electromagnetic spectrum. Cancer treatment is gamma rays. Bluetooth data connection is weak, so it actually uses radio waves. That's why it cannot penetrate walls. Optic fibers either use infrared radiation or visible light, so the available one here is infrared, not visible light. Security marking is similar to the fingerprints and the prints that are illuminated by ultraviolet rays, so here we use ultraviolet. Sterilizing food uses gamma rays to be able to kill the viruses or bacteria. Wireless internet, we can use radio waves or microwaves. Since radio waves have limited range or limited distance, microwaves can travel more distance, so the routers which have more power or can reach longer distances use microwaves, but it is mostly radio. Part II says state the approximate speed of radio waves in air. As in vacuum, it is the same, 3.0 times 10 to the power of 8 meters per second. Question B says figure 5.1 shows successive crests of a wave after a plane wave has passed through a gap. On figure 5.1, draw 3 successive crests before the wave reaches the gap. So in order to draw it correctly, we need to measure the distance between these circles, which is the wavelength of the wave, and we have to keep that distance the same. So we have here the distance between the wavefronts is 1 centimeter. So we mark equal distances. So we have 1 centimeter here, 1 centimeter here, here, and here. We need 3. And we're gonna draw a guideline for ourselves. So we can use a protractor to draw perpendicular lines on that guideline. So we have before the barrier, we have this part here, and we draw a vertical line. We move the protractor again, another vertical line, and the last one. So now we are sure that the wavelength did not change, and we're drawing the lines perpendicular to the original direction of the wave, which was horizontal. And now you can either choose to remove this line or keep it as a reference or as you're working. Either way is accepted, but this is the general shape of the waves. Part II says figure 5.2 shows a much wider gap. A plane wave of the same wavelength as in BI is incident on the gap from the left side of the barrier. On figure 5.2, draw 3 successive crests of the wave after the wave has passed through the gap. So on the right side, we need to draw less diffraction. So first, as in the last question, we draw the direction of the original wave as a guideline, and we mark 1 centimeter apart markings to draw the waves since the wavelength did not change. Then we use the protractor to draw 90 degrees on these points, lines that are equal in size to the gap. So this is the first one, move to the next, and we draw the second one, go to the last one. The question required 3, so this is the third line. But this is not the end of the diagram. We have to add curves to the edges of the lines, but the edges must have increasing in size curves. So like this, approximately like this, and the other side similar to it, increasing in size. So the fraction decreased because the gap is now wider than the wavelength. Question 6 says figure 6.1 is a full-scale diagram of an object O and its image I produced by a converging lens. The lens and its position on the principal axis are not shown. On figure 6.1, draw a single ray to locate the position of the center of the converging lens. So we can use the ray that passes through the optical center and continue straight without bending or changing direction. So we draw one line from the top of the object to the tip of the image, and this straight line should pass through the optical center. So the intersection here is the optical center. And then a line to represent the position of the lens and label the line L. So the lens should be a vertical line or perpendicular to the principal axis. So we can use a protractor in this way to draw a 90-degree line on the principal axis, and we call that line L. Part B says determine the focal length of the lens by drawing another ray on figure 6.1. So the other ray is parallel to the principal axis. So we can also use a protractor here to draw 90 degrees on the lens to make sure that the line is drawn correctly, and a ray from the object to the lens, and from that point we connect to the image. So we use the ruler and we connect to the image. This straight line or ray passes through the principal focus or the focal point. So this point is the focal point, and we need to measure this distance from the center of the lens to the focal point. So again, we use the ruler and measure this distance, which is approximately 2.1 centimeters. So the answer is 2.1 centimeter. Not everyone will get the same distance, by the way, and we also should label the arrows, the directions of the light rays on the diagram. Part C says the object is moved 2 centimeters closer to the lens, and the focal length was already 2 centimeters. So now the object is between the focal point and the lens. In this position, the image will be virtual, upright, and magnified. So it's used as a magnifying glass. State 2 changes to the characteristics of the image. It will be virtual and upright, since the image was already magnified in the question. So it will not be a change that the image is now also magnified. So we just write virtual and upright. Question 7a says draw the circuit symbol for a potential divider. A potential divider is basically a variable resistor with a slider, and we can move the slider. So we draw a rectangle and a pointer arrow on the top. That's a slider. Figure 7.1 shows a circuit. Calculate the value of V out when the value of R is 3 kilo ohms. So we have here 3 kilo ohms connected in series with a 1 kilo ohm resistor, and they are in series with a 6-volt battery. So the 6 volt is divided on the two resistors proportionally. So we can use cross multiplication. We can say that the 6 whole volts are provided to 3 plus 1, that's 4 kilo ohms. How many volts are supplied to 1 kilo ohm? So we multiply 6 by 1, then we divide by 4. That gives an answer of 1.5 volts. Part I says the value of R is adjusted until the current in the circuit is 1.7 milliamperes. Calculate the charge that flows through the circuit in 300 seconds. So we can use the equation charge is equal to current multiplied by time, or Q equal IT. We have 1.7 milli is 10 to the power of negative 3. Then you multiply by the time in seconds 300. That gives an answer of 0.51 coulombs. Question 8a says figure 8.1 shows a wire carrying a large current, and the current is going into a page. Part I says figure 8.2 shows a square card viewed from above, and the question requires that on figure 8.2 we draw 3 magnetic field lines that indicate the direction of the magnetic field and how its strength varies with distance. First, the direction. Using the right hand grip rule, since the current is going into the page, the thumb should be pointing into the page, and our fingers will close in the direction clockwise. So we need to draw concentric circles, and their direction is clockwise. In order to get all marks, we need to use a compass to draw the circles from the center of the current, or the center of the X marking in the diagram. And to represent the strength, we draw one circle, and the next one is close to it. So that's the second feed line, concentric circles, and another feed line, but much further away, to represent that the strength is decreasing by increasing the spacing between the field lines. And now we add the direction, which was clockwise, that we got using the right hand grip rule. So this is the shape of the diagram. Part I says the current in the wire increases and the direction of the current is reversed. State how these changes affect the magnetic field. So the field gets stronger and its direction is reversed. Increasing the current increases the strength of the field, and reversing the current reverses the direction of the field. Part B says electricity is transmitted at high voltage. Explain why high voltage increases the efficiency of transmission even with thinner wires. So we say when voltage is stepped up using a transformer, the current decreases, which decreases the power losses according to P equals I squared R. So when I decreases, the power also decreases with no need to decrease resistance using thick wires. So since I is already decreased, we do not need to decrease R also in the equation. Question 9a says an experiment directs alpha particles at a very thin sheet of gold foil. Most of the alpha particles pass through the thin foil in a straight line. State the conclusion about atoms from this observation. So this says that most of the atom is actually empty space. Part II says some of the alpha particles are deflected through angles less than 90 and few are deflected through 180 degrees, that's rebounding. State and explain two conclusions about the nuclei of atoms from this observation. So conclusion 1, which was the less than 90, that there is a concentrated positive charge, and the explanation is that alpha particles are also positively charged and are repelled by positive charges. Like charges repel. As for the 180 or the rebounding, it shows that there is a massive and tiny core, or has a small volume. That's why most alpha particles miss the core while traveling, and the ones that hit rebound. The ones that are directed straight towards the core or the nucleus, they rebound in the opposite direction. That means that the core has a much larger mass. Question B says a source contains a radioactive isotope of strontium. This isotope decays by emission of beta particles. The half-life of this isotope is 29 years. State the change in the nucleus which occurs when a beta particle is emitted. So one neutron changes into a proton. That's what releases the beta particle or the electron. Part II says the initial mass of this isotope of strontium in the source is 25 micrograms. Calculate the mass of the strontium isotope that decays in 87 years. So we have the half-life and we have the total time of the experiment or the investigation. So we divide the total time by the half-life to know how many half-lives we have. So we divide 87 by 29. That gives an answer of 3. So the decay is repeated for 3 half-lives. The initial mass was 25. Dividing that by 2, it's 12.5. That's the first half-life. Second half-life, we divide by 2 again. We get 6.25. Third half-life, we divide by 2 again. We get 3.125 micrograms remaining. We do not want to know the remaining amount. We need to know the lost amount or the decayed amount. So we subtract 25 minus 3.125. That gives an answer of 21.875, which we can approximate to 2 significant figures according to the question's numbers. So we have 22 micrograms approximately. Question 10a says figure 10.1 represents different positions A to H of the moon as it rotates around the Earth. State a position of the moon where an observer on Earth sees 1. There is a quarter moon. 2. There is a full moon. So a quarter moon from Earth, we need to see half the moon is illuminated. So the light is here and the other side is dark. So it's either A or E, or we can just say A and E. As for full moon, it happens when the Earth is in between the sun and the moon. So light from the sun illuminates the moon from all sides, and this whole area is seen from Earth as a complete circle. So it's G. So we write here G. Part II says state the approximate time taken for the moon to orbit the Earth, which is 1 month, or we can say approximately 28 days. Question B says the average distance of the Earth from the Sun is 1.5 times 10 to the power of 8 kilometers. Calculate the average orbital speed of the Earth in kilometers per hour. So the speed is calculated distance over time, but since the orbit is an approximate circle, it's elliptical, but it's an approximate circle, we use 2 pi r, and then we divide by the periodic time. So we have 2 pi, and we need the distance to be in kilometers, so we leave it as it is, 1.5 times 10 to the power of 8, and we divide by the time. The time for the Earth to complete one cycle is 1 year, which is 365 days, and each day has 24 hours, since we need the time to be in hours. And the answer is 107,588.7895. We approximate that to 2 significant figures or 3 maximum. So we can write the answer as 1.08 times 10 to the power of 5 kilometers per hour. Or to 2 significant figures, that would be 1.1 times 10 to the power of 5. Part double I says the speed of light in a vacuum is 3 times 10 to the power of 8 meters per second. Calculate the time taken for the light from the sun to reach the earth. So we had the distance is 1.5 times 10 to the power of 8 kilometers given in the question, and the speed is also given. So we use time is equal to distance over speed. So 1.5 times 10 to the power of 8, but the answer should be in seconds and the speed is in meters, so we convert this to meters, times 10 to the power of 3 from kilometer to meters. Then we divide by the speed 3 times 10 to the power of 8. These two will cancel out, and we have 1.5 times 10 to the power of 3 over 3. That gives an exact value of 500 seconds. Question 11a says, state the condition required for a protostar to become a stable star. So this happens when the pull of gravity inwards on the particles is balanced by the heat pressure outwards. So we have two opposing forces that cancel each other or balance each other, so the size of the star becomes constant. Question BI says define the Hubble constant. We can use the equation that the relative speed is equal to the Hubble constant multiplied by the distance from Earth, and we get the Hubble constant is equal to speed divided by distance. So we can say that it is the ratio of the relative speed to the distance from Earth, since these are calculated according to the position of the Earth. Part double I says the current estimate for the Hubble constant is 2.2 times 10 to the power negative 18 per second. State the equation which gives an estimate for the age of the universe. So the age is equal to 1 divided by the Hubble constant. Part triple I says calculate an estimate for the age of the universe. So using that, t is equal to 1 over h. We divide 1 by 2.2 times 10 to the power of negative 18. We get an answer of 4.54 recurring times 10 to the power of 17. We can approximate that to 4.5 or 4.55 times 10 to the power of 17 seconds. So this was the end of the exam. I hope you enjoyed this video and it was useful to you, and don't forget that to be able to solve any question you need to solve more questions, so your mind is kind of adapted to the type of questions or the type of tricks in the questions, or it helps also to memorize all the equations and all the definitions. So good luck, and I will see you in another video.